I'm Stefan Breuers. This work with Shisha Yang, Markus Matthias, and Bastian Leibel from RWTH Aachen University. So the problem is multi-object tracking. What is multi-object tracking? We have a video sequence like here on the left with potential positions of pedestrians resulting from a pedestrian detector. And as you can see, these detectors are noisy. You have some false alarms, you have some missing detections. And the goal of multi-object tracking is to get rid of this noise and to assign a unique ID, a unique track here represented as color, to each person individually. And so the problem is there are many different methods for multi-object tracking. Like you can here on the screen, see here on the screenshot of multi-object tracking benchmark mod challenge. There are, for the video you have just seen, 45 different methods. And our question was, is multi-object tracking saturated? Do different trackers make different mistakes? Or can we get a better result through fusion? So talking about different trackers, different mistakes, here are three example methods. Continuous energy minimization, CEM, from Milan et al. The dynamic programming approach by Pirzijavac, and the urban tracking by detection framework by Geiger. And let's have a look at these different methods. Here on the left we can see and different scenarios for these methods. On the left we can see the DP method that fails at filling holes when a detection is missing, while the TBD tracker does it right, and at least for the woman, not for the child unfortunately, but at least for the woman, get a consistent track, consistent ID. So you could say, yeah, then let's not take the DP tracker, let's take the TBD tracker instead. But extreme interpolation can also be a disadvantage. Like if you compare it to the CEM tracker on the left here, in the scenario B, if you stick to detections and like the CEM tracker on the left fails with this interpolation and hallucinates a bit. You get this ghost track that goes from the left to the right, while the DP tracker sticks to its detections, and this results in less false positives. And so now we have seen two strengths, two weaknesses. Let's look at the third scenario, scenario C. The CEM tracker also has a strength with this interpolating. Like on the right you can see the woman with the child stroller gets a consistent track. It stays green all the time, a unique ID. And while the tracker TBD on the left, you can see that the ID switches, the color changes, and the CEM tracker does it right, and you get less ID switches. So it's like rock, paper, scissors a little bit. We have three tracking methods. Now the question was, can we exploit the strengths and weaknesses of the different trackers? By fusion. You have an output of n trackers in this case, and a naive approach would be, okay, we take all the boxes, all that we have, and perform union on it. The good thing here is we fill up all the gaps and get way less false negatives. The problem is all the errors, all the false positive bounding boxes, they add up, and in total we increase more errors, increase more false positives than we decrease the false negatives. So let's come from the other side. Intersection, we take only those boxes in our fused results where all the trackers agree. Here it's the other way around. You fail at filling the gaps, you get way more false negatives, but you're very certain about the boxes you have and have less false positive. But again, the balance is not guaranteed. You introduce more error than you decrease errors. And our approach was the best of both worlds. And it's a learning-based approach where you first classify the false positive, a bit like in the intersection, and then merge the results to combine all the strength of the trackers. And this way get less false negatives. And some of the error balance is guaranteed. You do not introduce more error than you decrease error, and in total the general tracking performance increases. And for more detailed discussion, see you at the poster.